Hey, good morning. Thank you all for coming at such an early hour. Today I would like to talk to you about zero downtime PostgreSQL upgrades. A few words about me. I'm Alex. I work as a database reliability engineer at GitLab for a bit over 2 years right now. The 8 years before, I worked at a PostgreSQL and open source consulting company. And overall, I use PostgreSQL since the mid-2000s, and I'm into Linux and open source since the end of the 90s. Yeah, today I would like to talk with you about how we execute PostgreSQL major upgrades at GitLab with zero downtime. And I would like to do so by answering a few questions. First one, PostgreSQL upgrades. How do they work and why are they hard? So why do we need to talk about them? How did we perform upgrades in the past? Why did we need to improve on that? And how we improved on it. First, a little thing about my clickbait title. What is zero downtime? For me, it means all services needs to stay available to the end user. But it's not a Boolean. It's not a true or false, because each service and each action in the service has a certain response time. If a user clicks a button, the result is not instantaneous. If you have a great, snappy application, it maybe feels instantaneous to the user, but it's not. Yeah, it may take 100 milliseconds, but it's not a Boolean. You can't say it's zero or not, because it's never zero. There's always a latency. And there are different methods to define what latency is acceptable and what's tolerable. What we at GitLab use, it's called the AppDex. It's the Application Performance Index. It's an open standard on how to calculate that. If you're super interested, you can read the Wikipedia page. But summed up, you're looking at all of your requests or representable sample of your requests, and you define thresholds. So what's a satisfactory result? So the user clicks a button and it feels snappy and instantaneous. That makes the user happy. That's the satisfactory limit. If the user clicks a button and it takes a little while and it's not feeling snappy, it's feeling like walking to a tar pit, but it's still like usable, that's tolerable. And if the user gets really annoyed and maybe retries the action, that's frustrating. You have to define these thresholds for all your services or your actions. And then with this information, you can calculate the performance index. And that we have for all our services in order to have a single metric where we can estimate the user experience from. Well, we need this later to see if we improved on our user experience. Okay, why are PostgreSQL major upgrades hard? There are different kinds of services. You have stateless services like application servers. Upgrading them is pretty easy. You can upgrade a PG bouncer without any notice, with much effort, because it's a stateless service. And even if you have a stateful service like PostgreSQL, if you're doing a minor version upgrade, you can do it relatively nice as well, because all the state, all the heap files stay the same. But if you're doing a major version upgrade, the heap files do not stay the same. They normally don't have to be rewritten entirely, but their structure and metadata that has to change. And if you're having a large database, we normally at GitLab, we have 20 to 40 terabyte databases. Now we have more 20 terabyte databases and not one single anymore. But still, if you have relatively large databases, this takes time and consideration. There are different methods. The default method and standard one, for example, if you are using the official Debian packages, they come with PostgreSQL Common, and there are cluster management tools like PG Upgrade Cluster, and that's the default method there as well. And it has its pros and cons, but I go through it to show you why it's not the ideal thing for us. The first thing you have to do is you have to put your database in a read-only mode, because all changes you would do to the database during the upgrade process will be lost, so you would have data loss. So you start out with putting the database in a read-only mode, and then you can extract the data in a logical format with the tool pgdump or pgdumpall. In reality, you would not use SQL at the output format. You would use a slightly optimized internal format, but for the sake of the talk, we just say SQL, and the general performance is not so much different. So you have to take all your data, which is stored in binary format, you have to transfer it to a logical format, then you have to either write it to disk or directly transfer it to a new server. Both have pros and cons. If you write it directly to disk, you can use parallelization. If you are streaming it to a new server, you can't do that, or you have to manually build parallelization in it or use a special tool. And then on the new server, you have to read this logical data, and you have to put it in the internal binary format again. So both are quite compute-intensive operations and take quite some time. I guess for our database, the dump takes like 24 hours. And then after you have imported all the data in your new nice and shiny cluster, you have to recreate all the helping structures, because this is only transferring the raw data. You have no indexes, nothing around your data. So it's a nice thing if you have a small database, or if you have a 9-to-5 business and you don't work at night, you don't work on the weekend. It's a really safe option. And if you have the possibility to take a large downtime without a major problem for your organization, that's the way to go. It's reliable, it's easy, and you start out with freshly nice organized tables. You have fresh indexes, no bloat. And one really important thing, when you export and import your complete data, you are pretty sure it's sane, because everything gets parsed. Yeah, if this fulfills your need, you don't have to listen too closely to the other slides. I would go with this one. The next upgrade method is a bit more sophisticated. It uses the tool PG Upgrade, also a recommended method. And this tool gets a new release with each PostgreSQL release, and it knows which parts of the heap data changes and can rewrite your data on disk. Yeah, but this first step still stays the same. For PG Upgrade, you have to take your database down completely. If you would like to stay operational in a read-only mode, you can easily do that. You just have to create a standby, which you can use in read-only operation. Because if you would allow write traffic to this machine, you would lose all the user input or the user data during the upgrade. So only read-only is possible. And then you start PG Upgrade on your machine, going through all the heap files and rewriting where it is necessary. It's reasonable fast. It's reasonable safe. Yeah, it's not validating all your data. It's not going through all your data and checking if it's sane, and if it's for example, when you would do the PG dump and you are dumping a field that you can validate, like a JSON field, it gets dumped and validated, and on an input it gets validated again, so you would notice if it's corrupted. Here you don't have that side effect. It's quite simple, but one thing we noticed in the past, it could be that you have a performance degradation after an upgrade. And therefore, we had a process, I will show that in later slides, where after the upgrade, we had to check our regression tests for the database. So it can take a significant downtime if you're using this approach and you have additional checks and balances you have to do to your system before you can allow user traffic on it again. But again, if this method fulfills your need, you can listen to the other slides, but I would stick to that. Yeah, how did we do the upgrades in the past? We used the method I just showed, PG Upgrade. We created a second cluster from the backup. We synced the cluster, so now we have two carbon copy clusters. And we put GitLab into maintenance mode, and that's the problem. The whole red block is performed with downtime, so we took like half a Saturday of downtime for this. We used PG Upgrade on the primary to upgrade the data structure there. This is something that took us before like an hour, the PG Upgrade run. Nowadays, with the optimizations, it would take like half an hour, 20 minutes, half an hour. And then we recreated from the upgraded machine, we would recreate all standbys. And now comes the really downtime-prone thing. We needed to run a full regression and QA test on the application in order to assure that the new database is capable of handling our load. And why did we do that? The problem is if you are allowing user traffic back to your database directly, and you encounter a problem you cannot fix easily, you are in a really bad situation, because now you would have to decide, do I stick with the not performing application, or am I willing to sacrifice all the user data we got during the period we already allowed live traffic on the database? So a business requirement was that we are pretty sure the database and our whole setup is performing to our needs. And so this really increased the downtime period. But as mentioned before, if you are okay to take a downtime period, or you don't have direct user changes to your database, this method might be still totally valid for your use case. So why did we need to improve? Yeah, it was a large inconvenience for our users and customers. We did that on the weekends, but unfortunately, fortunately, we have users all around the world. And some of them are corporate users that only work mostly during their current 9 to 5 times on work weeks. But we have a lot of users who like to work on weekends as well. So taking off our application for half a Saturday is completely unacceptable. And even if we were not doing a PostgreSQL upgrade every year, but every second year, this single maintenance thing was responsible for the majority of our downtime. So that was definitely a pain. And it was such a pain that PostgreSQL upgrades were avoided, for they were so hurtful. So at the beginning of this year, we were still running PG12, for example. And how can you improve on that? How can you reduce the user impact? And like the first logical thing you could optimize, you could take the current process and just optimize it to reduce downtime. Yeah, as I mentioned, the biggest loss we had were due to the biggest downtime component was the excessive QA and regression tests. And you could optimize those tests that they are faster, you can make them shorter, or you can skip them entirely and have somewhat of a YOLO attitude to it. But as mentioned before, that was a business requirement to do it not this way. So we looked into a totally different method, which now with the cool new developments in PostgreSQL was available. And that is to use logical replication to upgrade asynchronously, so that we can do all the time-consuming steps of the upgrade while being still in full operation mode. And that's what we did, and that's what I'm walking you through. I will explain upgrade with logical application, a bit abstracted way, and then I will go through the steps we actually did. So first of all, we start out with our current database cluster. In reality, it's 1 primary and 8 standbys, around that, and our application talking to the cluster. Then we are creating a new one from disk snapshot, because that's the fastest method for us. And we brought them in sync during the standard physical replication. So we start out with 2 identical clusters, carbon copies. One is the main one used by the application, and one is the one we utilize for the upgrade. The next thing is we cut the replication, and now the cluster is a snapshot of the current production. The second cluster is a snapshot of the current production cluster somewhat in the past. We perform our upgrade on it, have all time in the world for this. And after the cluster is upgraded, we have all the time in the world to do checks and balances on it as well. And then after the upgrade, we can take our time to resync it. And that's where logical replication comes into play. Because with physical replication, you can only replicate from the same major version of PostgreSQL to the same major version. You cannot replicate from one version to another, or you can't replicate to a system that uses a different libc library, or you shouldn't. And that's the game changer here, that we are able to do that. Yeah, and after the cluster got into sync with the new cluster got into sync with the old one, you can pick a time which is convenient for you to do the switch over. This part, of course, causes a slight downtime because you have to switch all the connections from one to the other. But I will show you how we did it and what the actual user impact was, or if there was any. So logical replication. Why is not everybody using it for every upgrade? And at the beginning of the talk, I told you, if pgdump works for you, use it. If pgupgrade without bells and whistles works for you, use it. And the thing is, logical replication comes with some catches. The first is you cannot replicate schema and DDL. So all the DDL and all the schema is not replicated. You have to find a way around that. And by the way, I will talk about all of the four bullet points here in a bit detail right after this index slide. Next thing is sequences are not replicated, but they are heavily used in PostgreSQL. And each table needs a replication identity, unless you cannot use it. And the last but not least point, it's much more complex and prone to human error. Yeah, DDL is not replicated. That means you cannot start with an empty database and just logically replicate into it. You have to start with at least the schema. For us, it was not such a big problem because, as mentioned, we have a 20 terabyte database. We do not want to stream the whole 20 terabytes through logical replication. That's quite inefficient, quite the same as transferring all your data to SQL. So we just started with a really fresh, just a few minute old disk snapshot and used that as a starting point. So we do not have to replicate the schema, and a lot of the historical data also was not needed to be replicated. Schema changes, yeah, that's a bit up to you. You have to look at your application. Oh yeah, I have a slide on that. For schema changes, you have to look at your application. Does your application schema changes on its own? For us, it's quite good. We do schema changes. For example, we do partitioning. We create new partitions of tables and things like that. But we are not doing that as a result of a user interaction, so there's no user clicking a button and GitLab in the background decides, oh, now would be a good time to create a new partition. No, we have something called background jobs for that. And there's a flag in GitLab where you can just disable these background jobs. And we are doing right that. When our upgrade window starts, we are disabling all the background jobs, which has for us another benefit. Also, there are maintenance jobs, like explicitly calling analyze, vacuum for things, or calling re-indexes on certain indexes that are prone to bloat. And all these jobs I do not want to have during the upgrade, for they will increase load and write a headlog write on the database. So we just deactivate all these jobs at the beginning of the upgrade window, and we are fine with that. Sequences, that's kind of a bummer. Sequences are heavily used in PostgreSQL. If you're using a serial field, or for the MySQL users, you may know that as auto-increment, where you want to have just a new unique ID, preferably in a small integer. For a primary key, it's used often. You need something called sequences. A sequence is something in PostgreSQL that gives you a unique number, normally as an increment of 1, from a 64-bit integer, normally, if you're using big serial. Yeah, and this cannot be replicated, which on its own is a really big problem, because you would lose the information which of the IDs are already used, and you could get duplication problems. For us, the solution seems a bit like a workaround and was a bit hacky, but it worked quite well for us. Prior to the upgrade, we looked at our sequences, and we selected the information at which point each sequence was. So we got the integer value at which point the sequence was. And then a week later, we looked again, how did the sequences evolve? How many IDs did each sequence produce during 1 week? And we defined a threshold, how many sequences we could in max use during the upgrade. That's important because when we start with the new cluster and when we switch it to logical replication, it will no longer receive the information how many sequence numbers have been used on the primary cluster. Yeah? And we defined a gigantic threshold of 1 million, because that's something we would use normally more in a week than in a day or in a half day. But still, 1 million is not a big part of a 64-bit integer, so we weren't afraid to just increase the sequence count on the new machines by 1 million. So we would waste up to 1 million IDs from the integer space, but we made sure that we have no collision there. Is there somebody who would like me to explain it again, because I totally screwed up explaining the problem and the solution? Yeah, the problem is you get this. Okay, the solution is when you start the new cluster, when you bring the new cluster in sync with logical replications, you no longer get the information which sequences are generated on the primary, but they are generated in sequence. So if your current counter is like 1 million, they will give out 1,000,001, 1,000,002, 1,000,003. And we defined a large buffer on how many sequences could be generated in a week. And we used this to increment the new cluster. So the new cluster would start out not at 1 million, but at 2 million. Because for the usage as a primary key, it does not matter if they are really in sequence. It only matters that they are unique. Is that awesome? Thank you. So yeah, it's a really relatively simple workaround. You just find out what's a good value, and on your target cluster, on the new one, you just increase the sequence by this value. Replication identity. Each table needs either of these three things. It needs a primary key, then you are good. Another unique key which identifies each row of a table, or you have to fully track the full rows, so you are able to know when a row changes, and you have to replicate it to the new system. And the last one is quite performance intensive. And our solution was quite simple. We had to do nothing because, fortunately, all our tables have primary keys. So if you don't, you have to look into what you have to do. But having primary keys is quite cool. Anyways. Yeah, complexity. Last but not least, complexity. The logical replication method is quite complex. I oversimplified in the first overview, but there are a lot of things that can go wrong. You might have realized that when I explained the sequence problem. So it's quite prone to human error, and it's highly advised to automate all your steps so that you do them reliable and do not introduce new tiny human errors. And our solution to that is, as you might expect, we did a complete orchestration. So all actions all actions we could automate with Ansible, we did, and everything we couldn't easily automate with Ansible, we put in a quite tedious change request process, which we can execute reliable. And yeah, the most important thing is excessive testing. Yeah? When something hurts, you might need to do it more often until it's no longer hurting you. And for many things, if they hurt much, you have to do it a lot of times until it's not hurting so much anymore. And we did a lot of intense testing. We have 3 environments: a benchmarking environment, a staging environment, and production. So we could play around in benchmarking. We could, after we had a process, we could iterate on it in staging. But the cool thing here with this is you can do a lot of tests in production as well, because until the switchover, you can do all tests in production if you like, because you are creating a new cluster, you are making it sync from the old one, and if you're doing it somewhat safely, you can do it safe in production without impacting your users. So that's a really good one. We tested it in production, which also gave us great metrics on how the timing is for different things, and we could use the production load as an actual factor to see how much it will take for the new cluster to catch up and things like that. And yeah, as a little spoiler, the whole automation and also our change request issue template is freely available now. I was able to free it up last week, so I will put the links at the end. So if you're really interested, you can go through all of this in detail. Yeah. Now I will go a bit through our improved process. You saw the old one before with the large downtime. And you might remember this picture from before. Our first step is to prepare a new environment. And I apologize a bit, the new graphs are not looking as nice. They are directly from our change request issue, and they are generated by code. We have this feature in GitLab called Mermaid, or it's a markup language, where you can define different graphs in code in this case, it's a flowchart, and it's directly generated from the Markdown document, which is our change request. So I just screenshotted them. But therefore, you can nicely save your graphs in Git and iterate of them with your distributed team. Yeah, first step, we need to create a new environment. In our case, we create a new cluster from the snapshots, and from now on, we are calling the old cluster source and the new cluster target, because we are streaming data from source to target. We attach the new target cluster as a standby only cluster to the source. That means we have our main cluster, we have the target cluster, and it only consists of standbys. We have a standby leader that replicates the data from the primary cluster and then distributes it to all the standbys. Then comes the next step, the actual upgrade, which already is a bit more complex than in the overview. First thing, we needed to deactivate our normal automation. We have Chef running, so our machines are all provisioned by Chef. And Chef is quite good at configuring a machine and keeping it in this state. But at least as how we Chef use, it's not good into helping you transform a machine from one state to another or orchestrate that on multiple machines at the same time. So we are deactivating Chef, and as mentioned before, the orchestration for the upgrade we wrote in Ansible. We cleanly shut down the target cluster, the new one. And on the source cluster, we create a replication slot and a publication for all tables. That means now the source cluster, the current operation cluster, remembers at which point the target cluster is and saves all or keeps track of all the logical changes to the data, so the target cluster can later pull them from the source cluster. And for that, we need to remember the LSN, the logical sequence number. That's the point in time where we are hooking in again. Now we can start up our target cluster again. And it needs to, now it was down for some time, small amount of time, but it still needs to catch up to the, still needs to catch up to the source cluster again. And we are doing this still using physical replication. And now is the time where we can perform the actual upgrade. That means we are running PG upgrade on this cluster. That's the upgrade, but that's actually the most uninteresting part. You're running PG upgrade, and 20 minutes later, 30 minutes later, it's finished. But now we have one upgraded primary and a lot of not upgraded standbys. And we could now take a snapshot from the primary and reprovision all the standbys from this snapshot. But this would take not an hour or so, but significant time. And we use rsync. Rsync is a synchronization tool. The older people in the audience might remember using it for a lot of things. I definitely do. And you can use rsync to synchronize your data, and it's only synchronizing the files that have changed, and only looking at the files that have changed. But at this point, I would point out, if you're using rsync, make sure you're reading the docs and you're using the correct parameters, because if you're using the wrong ones, for example, if you are telling rsync to only look at the time a file has changed, it can be that the checks are not perfect. For example, it's not looking up to the millisecond, but only to a second change, and you could miss a file that has been changed. Yeah, just double check that you are using the correct parameters for rsync. You could also look in our automation to see which parameters we used. Okay, I'm not going through the parameters. We now have the primary upgraded. We used rsync to bring all these changes to all the standbys. So we have our target cluster upgraded to a new PostgreSQL major version. And now we need to let it catch up to the current production stand, because in the whole time we did this, users were working on GitLab, creating issues, doing stuff. And we need to get these changes to our new cluster. After we ensured that the cluster has a small replication lag, so all changes are replicated and it's keeping up to the current duration, we can continue. And the next step is to prepare the switchover. Now we have primary cluster, we have the source cluster, we have the target cluster has a new version, and they are in sync and replicating. Now we have to prepare for the future operation, because as mentioned, we have Chef, and Chef is good at keeping things as they are. And we have new roles that are able to maintain the new PostgreSQL version. So now we are changing in our configuration that the target cluster is no longer, in our case, PG12 cluster, but it's a PG14 cluster. And we run Chef now to see if it causes any unwanted side effects at an as early stage as possible. And during the testing cycle, we had to adjust a few things here to make that work, which is a domain thing at our place. So if you're not using this automation, you might not encounter that. But this was a cause of error, so we did that quite intensely and tested it a lot. We make sure Chef finishes and did not cause any unwanted side effect, and now we are disabling it again for the next steps of the upgrade. One thing that's not explicitly listed here, but you will find in the change request, multiple engineers will have open multiple dashboards and live viewing key metrics of the system. And here's a special point where everybody agrees that the metrics they are monitoring are in the given boundaries. And now comes the interesting part, the switchover. So we have the old database, we have the source database, we have the target database, and now we need to switch the application to no longer use the source, but to use the target. And in my oversimplified overview, it was just a simple step. For us, it was much more work. We have started by using the target cluster's standbys as standbys for the production load. So we put into our load balancer at first just one standby from the target cluster, put it in the load balancer, and now it was already serving read-only traffic for our customers. And then you can nicely see if you're comparing all the standbys, because they should get an equal amount of queries, you can already see, is this standby performing kind of like all the other ones, or is it performing significantly worse or better? And after the standby is in the loop for 15 minutes, and we watch the metrics, and we are quite happy how it performs, we put 50% of all the standbys, of all the target cluster standbys in the load balancer. So now at this point, around 50% of the target cluster standbys get production load. We again check the metrics if they are behaving as expected. If so, we put all standbys of the target cluster in the load balancer. So now in our load balancing, we have all standbys of the source cluster and all standbys of the target cluster. And then we come to this point, which says redirect read-only to target cluster. And in reality, that means that we are also removing all of the source nodes from the load balancing. So the load balancer will now only redirect read-only queries to the target cluster standbys, and nothing is directed to the source cluster anymore, and to the source cluster standby anymore. All write queries are still coming to the primary of the source cluster, because it's the it's the current primary anymore. It is the current primary. And now the majority of read load is served by our new target cluster, and that's the point where I give the mic to the quality engineering team, and they can perform their excessive QA tests. This takes up to multiple hours, but it's not a big problem because our application keeps running. There's at this point, no user impact whatsoever. And because the majority of traffic is served by our new cluster, we are quite sure that the cluster is able to handle the current production load and the QA test at the same time. So if this works, we are quite certain we have we have a high level of understanding that the cluster will keep up with production load. And in the past, this was the step where we had to cancel our upgrade the most. Yeah, if you might remember at the beginning, I said you could test every step until the actual step over in production, and we did multiple times. We needed to make improvements to our process, we needed to make improvements to our tools, and we needed especially improvements in our QA tests because they were so tight due to the double replication. Because if a write query comes to the primary of the source cluster, and then it's replicated to the standby leader of the target cluster, and then it's replicated to the standbys. And this increased replication lag caused our quality tests to fail. Sorry, I can't read the first number. Oh, thank you. This caused our quality tests to fail. And therefore, we had to cancel the upgrade and improve our quality tests that they are able to still work with a slightly increased replication load. Yeah, and if the quality team gave the thumbs up that everything works as expected, performance parameters are in line, we can switch over. And now the switch over is just redirecting the right traffic also to the target cluster because everything else is already there. And now comes the post step after the switch over, where the right traffic is switched over as well. We now have to check all metrics because the problem is this step is the point of no return. After this step, we cannot go back because everything that's written to the new cluster stays on the new cluster. With this method, we don't have any means of bringing the changes that have been done by our users to the new environment back to the old. So if you want to go back after this step, you have to decide that you want to lose everything your users did after the switch over. So that's why we were so finicky about deciding if the new cluster is now worthy to switch on it. So you see that whenever one of our checks fails here, we cannot go back. In the previous slide, whenever anything would fail, we would just roll back and nobody would notice. But at that point, if anything fails, we have to fix it. We kept a lot of engineers in the call to fix anything that would happen. Luckily, there was during the live upgrades nothing intense to do. Yeah. Then we re-enable our normal automation again. We already checked before that it does not have side effects. We enable it again. And then the cluster is monitored for quite some time if it's operating normally. And if it is success, the main upgrade finished. In reality, we have some additional jobs, like for example, with the upgrade to PostgreSQL 14, there are some improvements on B-tree indexes, and you can only utilize these improvements if you're recreating your indexes. So we had some post-upgrade steps where we would recreate indexes as well, or some of the improvements. And now the question, did we improve? I bring that back to you. We started out with a process where we had like 8 hours of downtime. And now the question, did we improve? I showed you this AppDex before, the Application Performance Index. And we have that for each service. For example, this one shows the Application Performance Index for the web service. And I'm pretty sure you can't see the scale. But here is 19 starts 99%. So the whole graph looks at the top 1%, and this is the normal noise. So there are normal events during the day which drop the AppDex, which that means the request time, the time a user action takes, is increased. That can happen due to high load, background jobs like auto vacuum, taking too much logs, things like that. And here you can see the window where we did the switch over. So you can clearly see we decreased our application performance a bit here, but it's much lower than the normal noise you would see during the day. Here you see the 9th of September, 8th of September, 7th, 6th. So during the work week, the normal operation, the normal spikes are much higher. then the upgrade spike. But you also see on the weekends we not have so much load, so on the weekends the performance stays quite same. But this is measurable, but not noticeable in a general. So it could be that there is a single user which clicked the button and it did not work, and that he clicked it again. But the percentage of actions that failed or took too long is so small that it's less than the normal noise level. This is the same metric for our API. So most users use the web interface, but also you can use our API to automate whatever you like. And we are measuring therefore as well. And you see the API is more used on the weekend, actually. There's a bit more noise, but still our upgrade was way less than the normal work week noise. And last but not least, that is our Git service. You could automate in your CI/CD that you're pulling repos, etc. And here as well, weekend has not so much use as the work, and the decrease in performance during the upgrade was less than the normal noise during a work week. Yeah. Now the question is, we have a process that improved quite a lot for us, but can we improve it further? And yes, we can do. I already spoiled that a bit. We were really unhappy with this fix-forward approach here, because after the upgrade, we have no choice into fixing all problems we encounter because we can't go back. And there's something you can improve on, and it's this part, because once you utilize logical replication, you can replicate from your old cluster, from your new cluster to the old one again, called reverse replication. So you have to set up your new cluster as the source and your old cluster at the target. And we already did experiment with that during the upgrade. So we actually made this configuration and streamed from the new cluster to the old one. But it was a recently added change, so we did not change the process in order to utilize it in a failure event. But we already tried it out to benchmark the performance and timing, and that worked quite well. And for our next upgrade, we will use that, and we will change the process that we do not have to fix forward. But if you encounter a larger problem here, we can go back to our previous cluster, to our old version, without losing a single user transaction. Yeah. And as mentioned before, I tried to open everything I just showed you. You find here some information about GitLab in general. You find our handbook. If you don't know what the GitLab handbook is, maybe super interesting. It defines us as a company, how we work, and it's a great thing to read into if you want to know how life at GitLab is before joining, for example. There's some information about our relation databases. There is here the playbooks, which we use for the whole orchestration. So you can download that. There's not a nice open source license added at the moment, but everything, the source is available, so you can at least read through it completely. And at this point, I would like Postgres AI. They helped us to develop and test the automation. That was quite nice. You will find the slide deck just after I left the stage. I will upload the current slides on the pgconf.eu's website. And when you're grabbing the slides, please feel free to leave me some feedback. There's also a comment section, so if you want to say something I can improve on, please feel free to put it in the text and still rate me good. And you can find some information about me as well. If you really like to dig into stuff, we are quite transparent at GitLab, so you can find, and yeah, we are using GitLab, the software, to organize GitLab, the company. So we are using our project management features to organize our work. You can find the main epic of the upgrade here. I put the full link in, and under this you find the epics for the different steps, so you can completely go through our thought process and how we develop the process, if you have some time to look into that. And the screenshots of the flowchart you will find here. I put the full link in as well. There you can find the source for the flowcharts. Yeah, if you have any question, you can ask me right now after I stop talking. You can approach me during the event, or if something comes to your mind later, feel free to catch up with me. And thank you.
All right. Just a really, really simple why 14?
Sorry?
Why PG14 rather than 15?
Yeah, great thing. We have a long-term planning on when to support which version. And if you want to read up, I made some suggestions to change it a bit, but yeah, unfortunately, we're quite conservative on that.
No specific reason, just...
No, no specific reason. We have a long-time planning. There's a spreadsheet when to use, and we would like to support only a small number of major versions for the product. So.
Yeah. Hi. Thank you for the talk. I have a question about the sequences. You mentioned that it's not supported like logical replication of sequences. There is currently work ongoing on that, but my question is like, have you considered using a type of a generator? I wouldn't say sequence, but a generator that actually doesn't require replication. I mean, like instead of using auto-incrementing value, using something like UID or something like that, because that would mean you do not need actually to, synchronize the state, right? So have you considered that, and what were the reasons why not to use that?
Yeah, I guess we talked briefly about that. So we briefly talked about if we can use something else than a sequence, you could use a unique ID, but that's a lot of work and would require a lot of change to the application. And the solution we choose, we didn't need any support by our application developers, and we didn't have to impose a change on millions of users. So this seemed, even if it looks a bit hacky, it seemed like the most simple solution to us, the most boring one.
Alex.
Thank you. Very interesting presentation. There was one bit which slightly surprised me, and I didn't completely understand. So you've upgraded your, you have a logical replication to your new PG14, and you start R-syncing to, was it some of the old read-only replicas? So I mean, I'm imagining that you had 10, you took 2 or 3, and you start pushing some of the load. But you're doing, I would assume, just in my head, you would build new machines. But you did rsync to those? That was the bit I didn't quite follow, why you were using rsync after setting up the new logical replica with PG14.
Okay, I guess I get your question. Your question is, why do we need to use rsync? Because the thing is, we upgraded primary is the wrong word. It was called the standby leader before, then it was technically promoted, and then we upgraded it. And now we have the upgraded primary, and we have a lot of standbys that still run the old version. And you cannot just run the upgrade on all machines. You have to, because they are not 100% identical, so you would normally have to take a backup from the primary and recreate all the standbys. And we speed up the process by using rsync, because you cannot upgrade the standbys on their own.
Okay, yeah, I'm getting it now. Thanks.
All right, time for maybe 2 more questions. All right. Alex, thank you so much for your time.
Thank you all for having me.